All right, good afternoon. So today we are going to be talking about beam deflection using singularity functions. And it's likely that you did not have much practice with this when you took your solids class. Whether you did or you didn't, I'm going to show you how to analyze beam deflections and get the equations into EES to make your life a little bit simpler. But first, I'll review the traditional approaches to beam deflection methods and finding the loads in beams. The deflection cannot be found unless we find the shear due to the loads, and then the moments, and then the deflection, and then the slope. And these are all integrals of the previous variable. So when we look at beams, beams are obviously members that are loaded transverse to their axis. And when we do machine design, we use beams all over the place. And so what is important is for us to understand the loads that develop inside the beams. Only then can we find the stresses. Okay, so we just use statics to do that. We basically sum forces on the beam element and go from there. Usually we will know what the forces are on a beam element, and from there we can calculate the shear stress. Once we have the shear stress as a function of the length of the beam, then we can integrate that and we can get the moment diagram. So just like a lot of mechanical engineering problems, it all starts with the statics. We have to get our free body diagram right. Then we can calculate shear, and then we can integrate the shear divided by EI, get the moment divided by EI, get the slope divided by EI, and get the deflection of the beam. Okay, and we'll talk more about that. Before we go too far, I'll just give you a quick review of shear and moment diagrams. And the traditional forces, we basically just, traditional approaches, we just sum the forces for a cross section. It's called the method of sections, where we cut the beam, find the reaction forces, find the shear in each section, and then find the moment. And then we can go from there to get our slope and deflection. Okay. All right, so this is just a simple example. This should be a review. If we have a simply supported beam here, okay, and we have two point loads and two reaction forces at 0.65 millimeters, 1.65 meters, then we can calculate the shear stress by summing the moments. The sum of the moments we can use to get an expression for the forces, and if we sum the moments in y, sum the forces in y, and sum the moments about point A as I alpha and MA, the acceleration and angular accelerations are 0. Okay, so it's a static problem. And so we can find here we have this distance times this force right here gives us 1800 Newton meters times 0.65. We do that for the other load, and we do that for the reaction. And then we can solve for RB. Once we have RB, we can solve for RA up here, and then we know our reaction forces. Okay, so then what do? You can find the shear. Okay, so in order to find the shear, what we do is we can slice the beam before this load here. We'll give a little bit of a slice across the cross section of the beam, and we sum the forces to 0. So we have this reaction force that we just found. We sum the forces with the shear force. Okay, so that means the reaction force and the shear force have to be equal to one another. These are our sign conventions for the both shear and moment diagram. So if we have a shear load that tends to separate the beam like this, and we call this positive shear. Okay, and that's the case that we have here. That's positive shear. And if we graph it, we see that this is a positive shear above the 0 axis for shear. Moment, you can remember the Cheshire cat if you want. A moment is if you're trying to make the beam smile, then it's happy. Okay, so that's our positive definition. Negative is if it's frowning. Sign convention here too is if you want to think about a left-handed Superman where the left hand goes out and the right hand goes back. Okay, so those are our sign conventions. So what we can do for the first section here is we can sum the forces. There's no acceleration, there's 0. Okay, so Ri minus V is 0, where Ra is the reaction at A. So we can say the shear is just equal to the reaction force at A for that section all the way until we get to that load here. And in that case, we have this second section. We can now sum the forces from there. So we can say Ra minus the load minus the shear is equal to 0. Okay, if we do that, we find the shear now becomes negative, and it's minus 427. So we went from this positive shear, now we go to this negative shear. And we can do the same thing for the third section here. We have the reaction minus the 2 loads minus the reaction shear. And that's if we cut the beam here right before that last load. And we can find the shear in that section is minus 1327.5, which should equal our reaction force. And we can make sure that we got that right. So if we go back to the previous slide, yep, indeed, the reaction at B is 1327.5. So those cancel out, and that shear load is brought back up to 0. Okay, so this is a shear diagram for different point loads. Now if we wanted to get the moment, then the moment is the force times the distance. Okay, so we found the shear for this section, and now all we have to do is multiply that load times the distance. Okay, so initially the distance is going to be 0, so the moment's going to be 0. And then as we move all the way on out to this load, we can get the moment, which is just the shear times the distance for this loading case. And it's going to cause a positive moment up here, all the way to this value. And then we have this negative shear times the distance. So then we start to take the negative moment. The negative shear times that distance gives us a negative slope. So we add those here in that second section here, just by multiplying the shear times x as x goes along. And then we do that again for this third downward force, which is again a negative shear, so we should get a negative slope in the moment diagram, and it comes all the way back down to 0. Okay, and this is the equations. This is just the force times the distance for each one of the sections. So we add that up. This is what it looks like if we put them on top of each other. And what you'll see here is we have these inflection points here in the shear, and they correspond to the max values here for the shear. When we cross that 0, we have this inflection point here, and when we have these step changes in value, we have the change in slope. Okay. Now, what if you have a distributed load? Well, if we have a beam here that has a distributed load, that has some force and some applied moment, and we look over here at this little section of the beam, and we come and do a free body diagram of this beam, this is the section of the beam here, then we have some moment on one side m, a moment on the other side m plus delta m, this part of the distributed load, which is w of x, and then this is w of x times delta x, so whatever that distributed load function is, if we have this distance delta x of this element, then it goes from here all the way up to w of x times delta x. And then we have the shear here on this side, and it's reacted by the shear on this side. So this is V, that's the shear there, and this is V plus delta V. And obviously everything has to balance out. So if we sum forces in y, we get the shear plus the distributed load times delta x minus the shear on the other side, which is V plus delta V, is equal to 0. So then we get the change in shear is equal to the distributed load times the change in distance, or we could say that delta V over delta x is equal to the distributed load. And if we took the limit as delta x goes to 0, we have the change in shear with respect to x is equal to the distributed load. Okay, so the change in shear is equal to the area under the distributed loading. Okay. Now, for the moment diagram, we can sum the moments for that differential element. Again, We sum the moments about 0. So that's summing the moments here about the middle, right here. Okay, we sum the moments about the middle. Okay, and then we have this shear on the left-hand side times delta x minus the moment minus the any distributed load times the distance for that load. So we can get an expression as the change in moment is equal to the shear times the delta x times the distributed load. So then we get delta m over delta x is equal to our shear plus the distributed load times the distance of that distributed load times delta x. If we take the limit as delta x goes to 0, then these delta x's goes to 0, and then we just have the change in the moment with respect to the change in x is equal to the shear, and from there we can say that the change in moment is equal to the area under the shear diagram. Okay, the change in moment for that section is equal to the change in area of the shear diagram. So you can check your numbers that way. If we have concentrated forces and moments, okay, if we have an applied moment here, M sub O, and we have a force here, F, we can sum forces in Y, do the static balance, okay, sum the moments, and do that balance, and then we can find that the change in shear is equal to the force for point loads. Okay, the change in moment is equal to the applied moment at that point. Okay, so anytime you have an applied load or an applied moment, it's just going to change the shear diagram and the moment diagram by that force or that applied moment respectively. Okay, so if you look here, the shear changes due to the applied loads, and the moment is the integral of the shear. Okay, and this area here should be equal to this change in moment here, okay, to that value. Okay. So if you were to multiply this area, if you were to calculate this area here, you multiply this number by the distance, you'll get this number right here. Okay. All right. So just an example, change in shear during the first section here is this change in shear. Delta V is equal to the applied force, the point force here from the reaction. The change in shear in the second thing is what it was minus the point load, so it drops in shear here. And then in the third sections, it's what it was, okay, minus the point load, and that's the change in shear here. Okay. If you look at the moment diagram, the change in moment is equal to the area under the curve of the shear diagram. So we can integrate these values, and we see that indeed the change in moment is 892.1. So it goes from here to here. All right, and then we can calculate the other intervals for the change in moment as well. Okay, so this is an example from the FE study guide for the Fundamentals of Engineering exam. So this is the problem. This is for the beam showed below. Where does the maximum moment occur? And then they have you do the static analysis. You just sum moments, sum forces in Y, solve for your reaction force, okay, and then find the place where you have zero shear. The place where you have zero shear corresponds to your inflection point for your graph or your max moment. Okay. So this should all be a review. And will show up again when you want to take your FE or when you want to design machines that have distributed loads, point loads, applied moments, etc. Okay. All right. So now I want to talk to you about singularity functions. Okay. And they look kind of nasty, but they really make life easier. And so we're going to use them in this class to describe the loading on beams, and they will make it easy for us to get our shear and moment diagrams and our slope and deflection. Okay, so it was first, I think, mathematician Macaulay, who created the Macaulay method to determine beam or shaft deflection. And all he really did is just say, we have these change in shear diagrams, okay, at these points, okay, and so we really need some functions that only apply when there's this point load, okay. And so he created these functions like that are these binomial equations with brackets to some power n. So Macaulay functions are when n is greater than or equal to 0. If you integrate the Macaulay functions, they follow the rules of ordinary functions, where you have the variable, you integrate it, and you get the variable to the n plus 1 over n plus 1 plus your constant of integration. So we use those for 0 and 1, and we can use these to define where the loading condition is for either a uniform load or a linearly increasing or linear increasing load. Okay, and the beauty of these function is that when the value of a, and that would be like the distance along a beam, when it is less than when x, which is, so a is where you might have something going on like an applied moment or load, and x is the distance along the beam, and it just says that, well, when x is less than a, then this function here evaluates to 0. Okay, and so all that means is that nothing goes on until you get to that point, and then after you get to that point, then your load is x minus a to the n, okay, for x greater than or equal to a. Okay, so then we have the ability with these functions to apply loads and at different points on the beam. Okay, now the extensions of the Macaulay functions are these singularity functions, and they include the negative powers of -1 and -2 into the integration here. So that's really the difference. The notation looks the same, but the difference is that for n equals to 0 and 1, they follow the rules of ordinary calculus integration. Okay, when they're negative exponents, then they follow the rules of operational calculus. And so if you look at the book and you look at the notation, they don't explain this, but this is the difference. Okay, and we use these for point loads or point moments here. And again, the beauty is when and these are a little bit different as well. Okay, so you see that these are defined on an interval, okay, for all the x's that are greater than a, and for these singularity functions, they're only defined when x is equal to a. Okay, so this allows us to define a point load. This allows us to define a distributed load. Okay, and this also allows us to define a point moment. All right, so that is the notation for those. Okay, now this is taken from your book, and we're going to get to the point in a second, but I think it's also important for you to know where these equations come from. So we can represent different loads with these functions. And so if we have a unit parabolic function, which is this function here, which is a Macaulay function when the power is 2. So that means when x is less than a, nothing happens. But when x is greater than a, we have this function here, which is a parabolic load. Okay, so we would multiply it by this, and then we'd get that that parabolic function. Okay, if we have a linearly distributed load, we can use a Macaulay function with the first order here. Okay, and we call all of these singularity functions. Okay, so when x is less than a, this is a beam, this is a cross section of a beam with a linear ramp load. When it's less than a, it's 0, and then when we get here, it's defined by this function. Okay, so the beauty of this, it allows us to write this in some code that allows us to calculate these loads and make life a little bit easier. If we have a uniformly distributed load, we can represent that with a unit step function, and that's when we have a 0. Okay, so this is a singularity function, and when we have this, when x is less than a, it's nothing. When x is greater than a, it's defined as 1. Okay, and then here we have this unit impulse function, which is x minus a to the minus 1. And that means when x is less than a, there's nothing going on. When x is equal to a, we have this point load. Okay, when x is greater than a, nothing else is going on. Okay, and then down here, if we have a concentrated moment, we can use this expression here, okay, which is to the minus power 2, and it's x minus a to the minus 2. Okay, and these are the definitions of the integrals. Okay, so these are defined by normal calculus. These are the Macaulay functions. These are the singularity functions, which are defined by operational calculus for these negative exponents. Okay, so and actually I think this might be Macaulay, because if you raise it the 0 to the 1, divide by 1, it's the same. Okay, all right, so let's talk about how we use those. Okay, so we use those as follows. So in this first case, we have a beam with an applied moment, and what we can do is we can define the loading function here. W is just the load, and we can define this whole load here by this singularity function, you know, where the applied moment is MO, and then we just have to write x minus a to the minus 2, because that corresponds to an applied moment. And the beauty of this is that we can then integrate the moment to find the shear here. We can take the derivative of the loading function, the integral of the loading function to find the shear, and then the integral of the shear to find the moment. Okay, and you can see what happens here to these exponents. We're just going from -2 to -1 to 0, and we've represented all those loading functions for this case. Now, if we have a point load, we have to use the corresponding equation for the point load here, which is to the -1 power. Okay, and then we can integrate that, and we get a 0. Get the 0 power, and then we can integrate it again, and we have these same equations. We just have to get these brackets and these exponents right. If we have a distributed load, we use the distributed loading function. Here we can integrate it, get the shear, and this is where we have to be careful here, because this is the case where we have, when we go to the when we integrate this, we're going to get the value here at the bottom when we go here. So as long as you kind of pay attention to which functions you're using for which case, you should be fine. But that's why there's a difference in this graph and the way that these are integrated. If we have a linearly increasing load here at some point, we go to that point A, and we use that function here where that load starts to be applied at A and then linearly increases. We can integrate that, get the power 2, bring the 2 down, integrate it again, and get our moment for that loading case. And in that case, we have the power 3 down to 6. So really the best way to see these is to understand them. Now, the real benefit of being able to do this is you can set up your equations once, and once you if you set them up properly, then you can get your shear, moment, slope, and deflections from your equations. And if you divide the shear diagram, the load diagram by EI, it's actually equal to the fourth derivative of the deflection. So if we integrate the shear diagram and divide it by EI, it's the third derivative of deflection. If we integrate the moment diagram divided by EI for the beam, where E is the Young's modulus and I is the moment of inertia for the beam cross section, then we can get the second derivative, and we integrate that again, and we get the slope. Okay, and if we integrate that again, we get the deflection. Okay. So that's what we can get all of this if all we really have to do is set up our loading conditions correctly and with the right singularity functions, and then we can get all of the the shear, moment, slope, and deflection diagram for the beam, and that's very important for design. Okay. Now the best way to do this is really to take your beam loading functions and actually put them in software, and that is the beauty of Singularity Functions. We can actually write software that can help us get those loads. That way we're not trying to do all the bookkeeping and get everything right by paper. Okay, so we have the pulse singularity function, step singularity function, ramp, parabolic, and cubic singularity function, and these are for point loads here. These are for distributed loads. Okay. Sorry, so unit ramp function. Okay, so ramp could be for a uniformly distributed load. Okay, and you can do that with a step function. Okay, so a uniformly distributed load is your unit step function. If you have a linearly increasing load, that's your ramp function. If you have a concentrated force, that's your pulse function. And then if you have a concentrated moment, it's your parabolic function. Then you can do higher orders. So this is the pseudocode. And so what I've done is, instead of having you guys kind of sort through all this stuff, I figured we could just work an example, and I could give you some example code. Okay, so what I'm going to do is take the example from the book, which is 3-4 A and B, and I will we'll walk through that. Let me show you the picture for that example. Okay, so this is the example from the book. This is a beam that's 10 inches that has a load, a distributed load that starts at 4 inches and goes to the length of the beam. The magnitude of the uniform force distribution is 10 pounds per inch. Okay, and so the beauty of these singularity functions is we can literally just write the equation for the beam's force, the loading function. All right, and that would be the reaction force at 1 here, and we write x minus a to the -1. So this is your unit pulse function. Here a is 0 because that's where it acts. It acts at 0. Okay, so we do x minus 0. So this is equal to 1 when x is equal to 0, which means that it's R1 and it's not defined elsewhere. It's 0 elsewhere. Over here we have this distributed load W, okay, and it's multiplied at x minus a. Okay, so as we go along the beam, it's undefined for x less than a. Okay, and this is our unit step function here, and so that means when x is equal to a, then it's defined, and we have a step up in the load, and that carries out through the rest of the beam. And then we have another load here, that second reaction force, and in this case it's only defined at L because of this function. This is our unit, this is our pulse function or impulse function. So you see this is the minus, these are -1. This is for the point loads here for the reactions at both positions. We have to put the x minus a values in for all of these. In this case, x minus a doesn't change, it stays at 0. In this case, A does change because we have this load that starts here at A and goes to the end. So we put that as x minus A. And then for the other reaction force, we put that in here at x minus L, because it's only defined at L. Okay. So these functions these singularity functions are very, very powerful, because then we can just integrate these. Okay. We follow the laws of the rules that we have that I showed you in the previous slide, and we go from R1 and we go from the pulse function to the ramp function here, and we go from the ramp function we go from the pulse function to the step function. Here we go from the step function to the ramp function, and then here we go from the pulse function to the step function, and then we have a constant of integration. If the loads are included in this equation here, then the constants of integration for the shear and moment, if we include the shears and moments that are applied, which we do by including these forces, then these constants of integration are 0. Then we can integrate these again to get the moment diagram, and you see we go from -1 to 0 to 1. In this case, we went from an impulse to a step to a ramp, and then from a step to a ramp to a parabolic function, and then again from a pulse to a step to a ramp. Okay, so these singularity functions, if we define them once properly, they take care of everything else. All right, so we'll stop here for this part of it, and then we're going to move over to EES, and I'll show you how to put these in software, and I'm going to actually share my program with you so that it will help you kind of be able to use it for your homework.